And it's my honor tonight to introduce tonight's distinguished speaker, Professor Gillian Heller. Professor Gillian Heller joined the University of Sydney as Professor of Biostatistics in 2020. She joined the as we call it CTC, the Clinical Trial Center. She coordinates the consulting and outreach activities of the biostatistics groups, and is involved in design and analysis across multiple trials. Prior to that, she was my boss at one time at the Department of Statistics at the time, and more recently, Department of Mathematics and Statistics, and now hopefully can call her my friend and a mentor. And from 2014 to 2019, Gillian was chair of the Biostatistics Collaboration of Australia, the BCA. She has over 30 years experience as a biostatistician and academic statistician. And tonight, Gillian will introduce something new to us, the new normal. And that's a very appropriate name in the year 2020, in a sense. And please join me in welcoming Gillian for her annual lecture.
Thank you, Thomas, for that kind introduction, and thank you for the invitation to talk tonight. Yeah, I don't know if I'm going to introduce you to anything new tonight. What I'm going to be talking about is a kind of nostalgic retrospective of the last 40 or 50 years of regression. Being nostalgic, it's going to be a personal view. It's going to reflect my own personal biases and research interests. So if I miss out on your particular research interests, please forgive me. But yes, the new normal, I think, is appropriate at this particular time, and hopefully I can give it a bit of a different meaning. So, Thomas, does this worked a minute ago when we tested it? I can use. Yep. Oh, now it's working. Yes.
Okay, now it's working.
All right. Good. Okay. So, why regression? Let's just look at the usual situation that we're familiar with, simple linear regression, and we know that in order to find the best fitting red line through the points, we take the vertical distances from the points to the line, and we square them and minimize the sum. So the least square solution comes from the early 1800s, Gauss and Legendre, but it took till the 1920s when Fisher pointed out that if you assume that the errors were normal, then that same solution coincided with a maximum likelihood solution. So normal linear regression, we've all seen this, but let's just write it down. Model assumptions, y is the sum of a fixed part, x beta, which is linear, plus the stochastic part, epsilon, which has the normal distribution with mean zero and constant variance. And the observations are independent. Now, let's think of those as the constraints of the model. What do we gain from those? What are the properties? Well, very nicely, the solution, maximum likelihood and least squares solution is in closed form and it's computable. Standard properties of MLEs tell us that they're asymptotically normally distributed and unbiased, and that because of their normality, they're actually exactly normally distributed and unbiased. They're also the best linear unbiased estimators. They consisted all of the good stuff about MLEs. Beta hat and S squared are independent, which gives us the distribution of our test statistics as chi squared T and F. That beta hat and S squared independent is interesting because here it's just a boring technical property that we need to derive the distribution of those test statistics. In fact, near the end of the lecture, I'm going to come back to that, and it actually gets pretty interesting. So just remember that. We've got our nice little statistic R squared, which summarizes the fit and parameter interpretation is straightforward. Now, this is the model that I learned as an undergraduate. That was it. That was all we had to know. Now, in 1972, now at the bottom I've got to credit Murray Aitken, who some of you may know. He's a well-esteemed Australian statistician. He's in Melbourne. And Murray was in the UK at the time that GLMs were developed, and he was instrumental in their development. And Murray wrote a history of the GLIM statistical package in 2018, and I've taken this quote. He said, theoretical and applied statistics were both convulsed by the publication of the GLM paper by Nelder and Wedderburn in 1972. Now, if you know Murray, Murray is the most softly spoken, polite person you have ever met. And if Murray says that they were convulsed, you know that that was a revolution. Okay, this really did change regression analysis completely. And so there's the paper by Nelder and Wedderburn. Wedderburn tragically died at the age of 28, a few years after this paper was published. Nelder went on to dominate British statistics and passed away 10 years ago. It's interesting, the keywords there aren't necessarily keywords that we would have thought about. Contingency tables, inverse polynomials, just some strange things there, but the world has changed. At the bottom there, this morning I looked up, Google Scholar had 8,620 citations. So what is the GLM? Model assumptions, then the YRs are independent with distribution from the exponential family, which includes, I've got them listed there, normal, Poisson, etc. So all those well-known distributions. Negative binomial, I've got in brackets because technically it's not in the exponential family, but for fixed value of its dispersion parameter, it is. So negative binomial is usually treated as part of the GLM family. So the exponential family is parameterized with the mean mu and a dispersion parameter phi, which differs from distribution to distribution. And we put a linear model on the mean mu through the link function g. And then it has the property that the variance of yi is your dispersion parameter phi times some variance function, which depends on the distribution itself. So we're hugely freed up from the constraints of the normal linear model. We now have a list of 6 distributions rather than 1 that we can choose from. We still have a linear predictor, x beta, but we've got that link function g, which means that we can have a multiplicative relationship, for example, with a log link. And so just notice the dispersion parameter is constant, and then we still have independent observations. Now, what happens to the properties? Well, the MLEs, the beta hats look similar compared to the MLEs of the normal model, excepting it's not quite the same. Beta appears in the matrix W and the vector Z, and so the solution is iterative. However, it was computable at the time. Remember, we're talking 1970s, and computing was quite different, and it was doable. That was the revolution. That here was a model that was substantially freed up from the constraints of the normal model, and it was doable in terms of computing power at the time. The betas, because they're MLEs, they have the standard properties of MLEs, asymptotically normal, unbiased. Again, I'm coming back, MLEs, beta hat and phi hat are asymptotically uncorrelated, which may not be a property that's familiar to you, but I'm going to come back to that much later in the talk. And the parameter interpretation is mostly straightforward. Now, I say mostly, it depends on your link function. So if your link function is identity or log or logit in terms of logistic regression, then you can write down an easy interpretation for beta. If it's not, for example, if you have a square root link, you can't write down what is the effect of an increase of 1 unit in x. So depending on the link, the parameter interpretation can be straightforward. Now, implementation was GLIM. Now, those of you probably looking around this room, you're probably all too young to have used Jake, even Jake is too young. Matt is definitely too young. Okay, I'm the oldest in the room. Yeah, GLIM was the most clunky package you have ever met, and I'll just add a personal recollection here. So 1970s, I did my undergraduate and then postgraduate study at the University of Cape Town, which you may know is at the southern tip of Africa. In those days, for all you young people out there, there was no internet, there was no email, and news traveled slowly to the southern tip of Africa. While I was undergraduate, there was a master student in our department by name of Trevor Hasty. And Trevor then went off and got into the PhD program at Stanford. But whenever he came back to visit South Africa, he would always come back to his old department and usually give us a talk. So this is early 80s I'm thinking of. I was early in my academic career. I think I was possibly still doing my PhD at that stage. Trevor came and he said he's got something really exciting and he wants to give us, I can't remember if it was a half day or a full day workshop, but it was something really important that he had to tell us. And that was that there's this exciting new methodology called generalized linear models and this amazing software GLIM. And that was it. We were all totally excited. Now, computing in those days was mainframes, right? Desktop computers hadn't made an appearance. So we were working on this UNIVAC mainframe and you sat at your terminals and you typed in a command and the answer came back. And we thought that was fantastic. And that was GLIM. I dug out at that time, well, it had the standard exponential family distributions in it. It didn't have a negative binomial. You could write macros, the little programs. And I wrote a macro to estimate the negative binomial regression. And I actually dug out the other day, I found that code and it is just unbelievably horrible, so clunky. But at the time, that was revolutionary. It was doable in the computing that we had in those days. Now, when I wrote the abstract to this talk, I made some glib reference to the exponential increase in computing power, and I had no idea, as you know, when you write the abstract before you write the talk, and I didn't know if that was true. It just sounded right to me. So then I went to the internet and had a look, and yes, indeed, that was about right. I found this graphic. So the Y scale, the Y-axis is on the log scale. This is computing efficiency, computations per kilowatt hour. And there we go. It is definitely linear on the log scale. So there we have exponential growth. Here's the UNIVAC. In Cape Town, we had a UNIVAC mainframe. So, you know, mid-70s, we were still on mainframe computing. The DEC, a lot of people use DEC PDPs. The Cray was a supercomputer, which probably had the computing power of your mobile phone. I'm not exaggerating. The IBM PC made its appearance in the mid-80s, and that was the first of desktop computing. So just putting that up to remind you really how primitive computing power was then, which made the GLMs all that much more revolutionary because they were achievable computationally. Then arrived the mid-80s, and our friend Trevor Hastie and his colleague Rob Tibshirani from Stanford introduced generalized additive models. And what they did there was they took the GLM and introduced these smooth terms into the linear predictor. And that was great, because what they said was, well, the relationship between y and x may be something that you don't know. It might be something like a curve, and you may not want to specify a parametric form, but you may not need a parametric form. All you may need is a picture, and that's what GAMs do for you. So the SJs are either parametric or smooth functions, so they could just be x or x squared, or they could be a smooth function. And when you choose spline and the SJs as splines, then by the clever way that splines are formulated as these little basis functions, sum of basis functions, it turns out that you still have a linear predictor, which is really nice. So for parsimony, then a penalty is applied to the spline coefficients to damp them down so that your spline isn't too wiggly, and that gives you penalized splines. So this again really did extend the GLM to a much broader class of modeling. The SJs can be curves, something like growth curves. They can be spatial effects. They can be varying coefficient terms. They can be interaction surfaces. Well, not the way I've written it there, but they can be. And I'm going to put in one more thing here, which may not sound right. They can be random effects. Now, they're not random effects. They're smooth terms, but I'll talk about it again later when I talk about random effects. Mathematically, they are estimated by the same machinery. When your penalty is quadratic, then by the same token that the least square solution to the linear model is also the same as maximum likelihood when your errors are normal, your smooth terms with a quadratic penalty turn out to be, can be estimated with the same mathematics as random effects. So whenever we write a model with smooth terms like that, it can also include random effects. So here's a favorite data set of mine. It concerns Medicare data. There were 1,514 residents of the Piermont postcode in Sydney in 1994. And what we have is each resident, their age, gender, and the number of times they claimed from Medicare for a visit to the GP. So there's the data. I've color-coded by gender. And as you can see, there are a couple of individuals who were rather frequent visitors to the GP, going, about every second day. This one up here and this one over there. And those are kind of damping down the rest of our observations. So what I'm going to do is truncate the y-axis as 50, then we can just see better. I'm keeping those observations in the model, just not showing them. So there's the data, and we see a general trend upwards as you get older, you go to the doctor more, and if you put just splines through those, that's what we see. So as we would expect, for young adults, well, between the ages of 20 and 40, women visit the doctor more, then men and women converge, but with the number of visits increasing, going into old age. And I wouldn't pay much attention to the divergence here because it's based on very few observations. So that's a general picture. And so can we use our regression modeling to fit that? Well, number of visits is count, and so we would try Poisson, and I'll save you all of my workings, but Poisson, the data were over dispersed, but the negative binomial fitted. So what I did then was I searched around for a model. I used a log link and found the AIC told me that a quadratic X1 is age, X2 is gender, that a quadratic term in age plus gender gave the lowest AIC value. So that's our chosen model. And so there are the fitted values. So we're going to come back to that example. But let's firstly think about the modeling of phi, the dispersion parameter. Now, one of the assumptions of the GLM and the GAM is that phi is constant. Now, there's actually no reason for it to be constant. It could also vary with covariates. So Murray Aitken, who I've mentioned, in 1987 introduced a model, a normal model in which he put a log linear model on sigma, the standard deviation. At around the same time, in 1989, Gordon Smythe, who some of you may know from Melbourne, took the gamma model from the GLM family, and he put a model on phi, the dispersion parameter. And there were some others as well. This isn't, these references aren't complete. The other one that I'll mention is Rigby and Stassinopoulos in '96 introduced mean and dispersion additive models. And so they took the exponential family and they introduced modeling on mu and phi. And then they also introduced the smooth terms. So for each of mu and phi, you can have a linear part and you can have these smooth terms. And by the way, the x's so now you've got two models, one for mu, one for phi. The x's in these two models can be the same, or they can overlap, or they can all be different. And we'll see examples of those. So let's just look again at these mean and dispersion models. So that's the same model that I had on the previous slide. So just summarizing then, it's still the exponential family response distribution. We've done away with the constant dispersion parameter phi. That's now covariate dependent, and we've kept the independence. So what we can, the properties then, computation is, let's just say, more tricky. You've got to be cleverer about computation algorithms. However, remember, we've now moved to the mid-90s. By now, we have desktop computers, much more powerful computing, and we're computing in, I'm not sure by that stage if it was S or S, probably S at that stage, which then became S+. So computing now is starting to resemble much more of the computing that we know. So computation more tricky, but doable with the tools available at the time. The beta hats were asymptotically normally distributed unbiased as usual. MLEs, well, I keep coming back to that, beta hat and phi hat are asymptotically uncorrelated. Parameter interpretation, I'll just say, is more difficult. You can have a covariate that appears in the model for both mu and phi, right? So what is the effect of X if it appears in both parameters? And also if it appears in a smooth term, what can you say about it? So it's getting more tricky. So let's look at our GP visits again. That's where we got up to last time. We only specified a model for mu, but now we can add on to that a model for phi. So I've simply put a linear term for age and gender, tacked that onto each of the models for mu that we had before. And we can see by these AICs here, they're all less than the AICs of the models without a model for phi. So, you know, even just doing this, putting in these terms in the simple form like this absolutely improves the model. So now we can do even better by looking for better models for phi, and I won't take you through the blow-by-blow computations, and I'll just show you that the best model is the bottom one, where you keep your quadratic model for age in log mu plus gender, and then for phi we have the smooth term in age. So there's the fit. It looks fairly similar to the previous fit, but if you put them side to side, you can see the differences. If you want to look at the effect of age and gender on each of the parameters, you can look at partial plots. And so we see the top left plot is the partial effect of mu, of age on mu, and as we know, that's quadratic. The bottom left plot is the partial effect of age on sigma. And yeah, that's it. So what is the effect of age on the mean number of visits? Well, on the distribution of the number of visits. Well, with the effect on sigma, it's a little difficult to say, but at least we know the effect on the mean is quadratic. Okay, so moving along then. So now we're up to, we're still sticking with the exponential family. We can model each parameter, mu and sigma, and we can have smooth terms. That's where we're up to. What about correlated observations? Well, this paper by Laird and Ware in '82 was a seminal paper that introduced, well, random effects did introduce before, but this really popularized them in statistics with random effects models for longitudinal data. And what this was, they used a normal response distribution and a normal random effects distribution. Now, I'm not going to go into the mathematics of random effects. We all know what random effects are. I'll just say that they allow us model structures, random intercepts, random slopes. They allow us longitudinal designs, hierarchical models, and we can get complicated. They work. Random effect to me is a bit of an odd construct in that if you think about it, it doesn't actually describe what's happening. But it works. It successfully models correlation between sampling units, and it corrects for standard errors in the right way. So there we have a method that works. They can be included in all of the models we've discussed, and as I've said before, mathematically, they're actually treated in the same way as penalized spline terms. So a quadratic penalty equates to a normal random effects distribution. Now, they're not the same thing. They are not equal, but it's just a convenience that we can treat them the same mathematically. And also, I'll just mention that generalized estimating equations and copulars are other ways of introducing correlation. So there we have it. We now can throw away our independence assumption. We can introduce dependence between observations using either random effects or, if we want GEs, or copulars. So then we come to the last important development, and that was then moving on to 2005, Rigby and Stassinopoulos introduced the generalized additive models for location, scale, and shape, called, or shortened to GAMOLs. So what they did here was they did away with the exponential family restriction, and the response distribution is any parametric distribution as long as you can compute it. And so that really does free us up. It's still parametric, but as long as you compute it, that's fine. It can have up to 4 parameters, and each of those parameters can be modeled. And in the same way, there can be a linear term and then any number of smooth terms. So this is, it's hard to imagine how much more flexible a model can get than this. We've done away with the relationship between the variance and the dispersion parameter and the variance function. That doesn't exist anymore. The parameters, so they're Rigby and Stassinopoulos call them in order mu, sigma, nu, tau, and that's kind of stuck. Mu is a location parameter, usually. Sometimes it's a mean, sometimes it's a median or the mode, sometimes it's something else entirely. But it's always favorable to have a parameterization of the distribution where your parameter mu is a location parameter, because that's what you want to model. Sigma is usually a scale or dispersion parameter, so it could be standard deviation or the variance, or it could be something else entirely. And nu and tau, if they exist, are some other shape parameters. So what are the properties? Well, extremely flexible modeling. You can really do anything. The sky's the limit. Estimation is done by penalized maximum likelihood, which I've mentioned before. There's also, if you want, Bayesian estimation, and I'll mention the package later that does that. The MLEs are asymptotically normal, unbiased, as usual, as they should be. They're not uncorrelated. And we'll talk about it again. Now, model selection, and we'll come to an example of this. Model selection is complex. You've got to choose a response distribution, and you've got to choose a model for each distribution parameter. And that's not simple. Parameter interpretation is not even more difficult, it's complex. But I'll show you something that'll help with that. So just to mention software that we have, well, GAMLs, Rigby and Stassinopoulos, and I myself, I've been involved with Mikis and Bob, and in fact, we've written some books on the subject together. BAMLs is a lesser known package. It's written by Umlauf, a group, and Klein, Salas, and some others. They're German statisticians, and they're working together with Rigby and Stassinopoulos, but it's the Bayesian estimation for GAML's models. VGAM by Thomas Yee in Auckland is a package that's been developed completely independently. I'll just mention GAMLs has over 100 response distributions. And if you have a distribution, if that's not good enough for you and you've got another one, you can also define your own user-defined distribution. VGAM was developed completely independently and is a very nice package. Also, I don't know how many, but a large number of distributions. MGCV by Simon Wood is mostly exponential families. Simon has a few other distributions there, but not many. That's not his focus, but it's a very fine package with all sorts of capabilities in the smoothing area. Okay, so here's the second example of one of other of my favorite data. So I've got a few favorite data sets, and this is to do with fetal ultrasound. So ultrasound is used in pregnancy for two purposes. Number one, to identify fetal abnormalities, and number two, to predict birth weight, because very small and very large birth weights can induce complications. Now, if you look at the obstetric literature, there are a whole lot of weird and wonderful formulae that are in use for prediction. So based on the ultrasound measurements to predict birth weight. And so I'll just reproduce one called the Spinato equation after the author of that publication. So BW is birth weight, and they model log of birth weight. For some reason, they take log to base 10. And they take head circumference, and I always think AC is air conditioning, but no, it's abdominal circumference. FL is femur length, and then you get the product of abdominal circumference and femur length, and then DBD is days before delivery. That's just a correction for the time lapse till birth. And there are quite a few of those equations in the obstetric literature. And they were developed under the using classical linear modeling, that they didn't come from nowhere. So the question is, can we do better using distributional regression? So I've got data from the Royal Hospital for Women in Sydney, births between 2008 to 13. And these were 882 scans performed within 7 weeks of delivery. And so if we just look at the histogram of birth weights, there it is. It's mildly left skewed. And so the question is now, how do we select a model? We need to firstly select a response distribution. It's not obvious what to do. And then we need, whichever distribution we choose, we need to select a model for each distribution parameter. Now, I want to say what's important is we do not select the response distribution on the basis of that marginal distribution. That would be wrong, because the regression is it's the conditional distribution. We want to model birth weight conditional on covariates, and that may not be the same, may be similar, but it may not be the same as the marginal distribution of birth weight. So it's not good enough just to fit a distribution to the marginal. What we have to do is look at conditional distributions. Now, this is pretty ad hoc. There's no best way to do this. What I did was I chose the response distribution based conditionally on simple linear models for all distribution parameters. So I just stuck all of the covariates in just in their linear form, and then in all of the distribution parameters for all of the distributions that I considered. In Gamels, there's a function to automatically do that, and then and base the choice on AIC. Then I used forward selection for the model. So using that response distribution, I then selected the model for each distribution parameter using forward selection. And then I went back and checked. So then I checked the research. So then using those distribution parameter models, I went back and checked that the response distribution was the best one to use. So as I say, you know, give me n statisticians and they'll probably come up with n different models. This is ad hoc. I've said before, model selection is complex. But in any case, this is what I came up with. So the response distribution I chose was the Box, Cox, Cole, and Green, which is a 3-parameter continuous distribution on the continuous real line. There are some plots of it. So the parameter mu is a location parameter, which is approximately the median. Sigma is a scale parameter, which is approximately the coefficient of variation, and nu is a skewness parameter. And as you can see, the distribution is capable of both left and right skewness. So there's the model. And so we have in first column or second column, the model for mu. And in the middle column, the model for sigma. And the last column, the model for nu. So that's pretty complicated. It's a complex model, but the question is, well, does it do the job of predicting birth weight? Because that's the point. And so the answer is yes, it does. In the table at the top, I've looked at a prediction error using various measures, and the BCCG model, I've compared it to the normal, the Spinito model, and the BCCG outperforms on each of these measures. I've also compared predicted to observed values. For the BCCG model, I computed the predictions using cross-validation. And you can see the blue ones, that the Spinito predictions appear to be upwardly biased, whereas the black ones, our BCCG predictions, look much more accurate. So the answer is yes, it is doing a good job for prediction. But let's go back and say, well, what if we wanted to understand, to interpret the parameters? One of our speakers this afternoon talked about prediction versus interpretation. And this is exactly the point I'm getting to. The point of that model was prediction, but if we were interested in interpretation, how would we interpret that model? So if we take air conditioning, abdominal circumference, right? Take that. For example, it appears as a log term in the model for mu and nu, right? And then in an interaction with age, in mu alone, and that's it. Okay, but that's hard enough. Oh, sorry, and also in an interaction term with BPD, which is biparietal diameter, which is the diameter of the baby's skull. So that's pretty hard. How do we interpret that? Well, here we have some wonderful plots. So my student Stan has written an R package called disreg.viz. What it does is it takes covariate values and plots the PDF at those values. And so you can choose a range. So what I've done is I've chosen AC 20 to 40, which spans the range, and all of the other covariates at their means. And this is the PDF of birth weights. And I think that's pretty informative. What it's telling you, firstly, the distribution of birth weight changes from right skewed at the left end to left skewed up here, sort of symmetric in the middle, and then right skewed. And it's also a very good predictor of birth weight at those different values of abdominal circumference. The PDFs of birth weight are very well differentiated. So it's a very good predictor of birth weight. Maybe I'll move on. I've got some others, but I won't spend time on them because I want to get on to my next topic. Okay, and so there we have it. Parameter interpretation is complex, but with the aid of these visual tools, we can actually get a handle on that interpretation. So the last topic I want to talk about now, I've kept on banging on about beta hat and phi hat not being independent, or either they're independent under maximum likelihood or they're not. And this is what I'm coming back to now. And it's the concept of parameter orthogonality. Now let's take just a generic distribution with parameters mu and sigma, any distribution. Then it'll have MLEs, mu hat and sigma hat. And from standard properties of MLEs under standard conditions, we have the asymptotic distribution. And the important thing here is that the variance covariance matrix of mu hat sigma hat is the inverse of the Fisher information matrix, which looks like this. Now, mu hat and sigma hat are asymptotically independent if that the diagonal element of this matrix is 0. And in that case, mu and sigma are called orthogonal parameters. Now, what is the advantage? That sounds like a good thing. Why is it a good thing? Well, it means that the estimators, the maximum likelihood estimators based on that parameterization will be asymptotically uncorrelated, which gives you more stable computation and a regression advantage, which I'll demonstrate. Now, firstly, in the exponential family, we have a result which tells us the mean mu and the dispersion parameter are orthogonal parameters. So we're fine. Don't worry about any of what comes next if you're just thinking about the exponential family. Once you move outside the exponential family, then you do need to worry. What I'm going to do is show you some plots. Now, this is for the normal distribution. The plot on the left is the contours of the likelihood of a single simulated sample. The true value, mu, the black dot is the true values, mu is 5 and sigma 1. And so here's the sample, and the red dot is the MLE. You can see it's at the maximum, the middle of that likelihood. On the right-hand side, what I did then was I simulated, I think, 200 samples from that distribution. And on the right, I've got a density estimate of the distribution of the MLEs, mu hat, sigma hat. Right? And I've got here the correlation between them. So we can see that there's nothing going on there. there's no relationship between mu hat and sigma hat, and that's borne out by the almost zero correlation. And the gamma distribution, also in the exponential family, we see a similar thing. The likelihood looks a bit different, but also uncorrelated mu hat and sigma hat. Now, what happens when you move outside the exponential family? So remember the BCCG distribution that we used to model birth weight? There it is. And that looks interesting. On the left, the likelihood looks banana shaped, right? And on the right, it's like an avocado cut in half, doesn't it? With negative correlation, the correlation minus 0.13. So that is a bit of a concern for reasons that I'll talk about, but definitely non-orthogonal parameters there. The Poisson inverse Gaussian distribution is a favorite of mine. So it's a compound Poisson distribution or over-dispersed Poisson. I affectionately call it the pig. And so there we have on the left, again, the likelihood is sloping, which is indicating that it's non-orthogonal. And on the right, the correlation 0.31 between the MLEs. So non-orthogonal distribution. Now, here, this data set comes out of a clinical trial for a drug to control the number of falls in patients with Parkinson's disease. So in the treatment group, patients were given a drug to control the condition that leads to them falling, which is dizziness. And basically it worked. If you look at the treatment group, average number of falls was 3.4. This was over a, can't remember the period, but it doesn't matter. 3.4, control average number 8.7. Seems to have worked, but look what it's done to the variance. The variance in treatment 62, in control 30 and 88. So treatment has damped down the mean number of falls, and it's hugely damped down the variance. It's really done something there. If you look at the maximum number of falls, 49 against 358. So if we're thinking about models, we're going to need a model for the mean because there's a treatment effect on the mean, but you'd think we'd also need, there's a treatment effect there on the spread. And if we don't do that, we're not modeling correctly. So the Poisson inverse Gaussian distribution, there are several versions of it in the literature. The one that's in GAMLs is this PD, it's in terms of parameters mu and sigma. This is what it looks like, which is pretty awful, not very nice. This K here is a Bessel function, which is computable, but quite awkward. However, the mean is mu. That's nice. We can model the mean exactly. And the variance is this quite simple function, mu times 1 plus sigma mu. So sigma is a dispersion parameter, and we can interpret sigma as a Poisson over dispersion parameter. When sigma is 0, then the distribution tends to the Poisson, or the limiting form. However, unfortunately, mu and sigma are not orthogonal, and we've seen that in the previous plot. There is also an orthogonal parameterization of the pig. So if we keep mu, because we like to have mu as a parameter of the distribution, being the mean, but then we define a new parameter alpha, which is this nonlinear function of mu and sigma, then we can write down the distribution like this, which is, again, not very nice, but it is computable. So we've kept mu as the mean of the distribution, and the variance is now a much more messy function. But we have to put up with that. All we can say about the variance is that it has an inverse relationship with sigma. So sigma is some sort of inverse dispersion parameter. So if we look at the the likelihood plots for the orthogonal parameterization of the pig, well, we can see on the right-hand plot that we have in fact reduced correlation to about 0. So if we look at a model for the number of falls in this clinical trial, so typically in clinical trials, only the mean is modeled. Now I'm going to consider two models, a treatment effect on the mean only and a treatment effect on the mean and dispersion. And I'm going to call those the restricted model and the full model. So in the restricted model, we've got X is treatment. So we've got treatment in the model for mu, got log links, treatment in the model for mu, and nothing, just an intercept in the model for sigma. And log of t is just an offset for time because not all patients were in the trial for the same period of time. For the full model, we have the same model for mu, and we also have a treatment effect on sigma. So we estimate that model now, it's in GAML, so we just use the GAML software for this. And so in red beta 1, remember it's a clinical trial, so it's the treatment effect that we're specifically interested in. In the restricted model, the treatment effect is non-significant, which is surprising. And in the full model, the treatment effect is very different and it's significant. Now that's hugely bad news. In a trial, you know, that gives investigators the jitters. That they don't want to see that. That depends on the model, what answer you get. You know, are they going to register this drug or aren't they? So beta 1 is sensitive to the specification of the model for sigma, and that's not good news. So what we can do is do the same sort of estimation, but using the orthogonal parameterization. So we can again have a restricted and the full models in the same way. So now we're modeling alpha rather than sigma. And here's the result, and it works out really nicely. So beta 1 is very similar between the restricted and the full model, and significant in both models. So, or both beta 0 and beta 1 are robust to the specification of the model for alpha, and beta 1 had highly significant in both models. So you may say, well, that could just be an artifact of that data set. You need to do a simulation to confirm that. Now, I don't have time to show you that, but I'll just say that simulation confirms that when the parameterization is non-orthogonal, then misspecification of the model in one parameter leads to estimation bias in another parameter. It spills over because they're correlated. However, correct specification of the models in all parameters leads to unbiased estimation. So if you're using a non-orthogonal parameterization, you need to be careful that you're specifying all of your distribution parameter models correctly. Otherwise, you could be in trouble. When the parameterization is orthogonal, parameter estimates are robust to misspecification of other parameters. So it's not generally straightforward to find the orthogonal version of a distribution. I presented one version of the pig and the non-orthogonal and the orthogonal version. That's not, and that happened, that's the story in itself, but it's not that easy to find. And in general, one can't always find it. It's not always tractable. So the process involves finding a new parameter which leads to 0 off-diagonal elements of the Fisher information matrix. And that's a differential equation, which sometimes you get a nice solution to and sometimes you don't. So current work with my PhD student Stan is finding numerical solutions when analytical approaches fail. So that's what we're doing at the moment. So to sum up then, that's the state of play that I'm going to leave you with. Properties of distributional regression are very flexible model. Basically, we can do anything with a parametric response distribution. Practically unlimited choice of distributions, smooth terms, random effects, spatial effects, zero inflation, censoring, truncation. It's all doable. Estimation, you can use either penalized maximum likelihood or Bayesian. That's all available. The MLEs are okay, excepting beware of non-orthogonal parametrizations, which I've just shown you. Parameter interpretation can be complex, so use visual methods in that case, and model selection can be complex. And at the moment, well, there's a boosting approach that I haven't even had time to get into, but boosting can be used as a means for model selection. Otherwise, it's pretty ad hoc. It's more an art than a science. Now, 2020 has been a difficult year. And so I thought I'd end off this lecture with a song. Now, I can hasten to assure you I'm not going to be singing the song myself, but I hope you enjoy this. And also, we did practice before, but I'm very nervous that the technology is not going to work. So bear with me. And if the online people don't hear it, apologies.
It ain't necessarily so. It ain't necessarily so that for models to be formal, errors have to be normal. No, it ain't necessarily so. My data had values, real skill, relationships, nonlinear too. But with spline approximation and box-Cox transformation, my data are more normal than you. No, it ain't necessarily so. Your deviance has to be low. Try less parameters, less alphas, less betas, then apply Akaike, although it sounds freaky, and less will be more, as you know. No, it ain't necessarily so. It ain't necessarily so that for models to be formal, errors have to be normal. No, it ain't necessarily so. No, it ain't necessarily.
It ain't necessarily.
It ain't necessarily.
It ain't necessarily.
Oh, it ain't necessarily.
Oh, it ain't necessarily.
Well, it ain't necessarily so.
That was Michael Greenacre and Gurdeep Stevens performing at the IWSM in Barcelona in 2007. They gave a wonderful concert. Michael, I don't know how many of you know him. He's a fellow countryman of mine from South Africa originally, but he's in Barcelona now, and he's also a musician. So that's all I've got for you tonight. Thank you.